So next we'll go for the calculation of percentage of tension steel reinforcement, that is denoted as PT. For that we have the formula 100 into HT provided divided by B into D. So don't get confused here. Here we need to substitute a value of HT provided. So this formula is given on table number 19 and page number 73. I will show. So this is the table number 19 of page number 73. So here the formula percentage of tension steel reinforcement, that is denoted as PT. For that we have the formula 100 into AST divided by B into D. So by using this formula we will calculate the PT. Same formula which is given on page number 73 I have written here. So substitute all the value. PT is equal to 100 into our AST provided value we got was 942.45 divided by B value is 300 mm and D is 350. After simplifying we will get our PT value as 0.89%. This is how we calculate the PT. So next we will go for the calculation of shear strength concrete, that is tau C, denoted as tau C. So for calculation of tau C, we by using the value of PT or percentage of tension steel reinforcement and FCK, by using these two value and with the help of table number 19 we'll calculate the tau C value. So we'll see, I will show how to calculate tau C. So by doing the interpolation method we need to calculate the tau C value. I will show how to do the interpolation. So this is the table number 19. So this column has the value of the PT value, percentage of tension steel reinforcement. So why we need to calculate the PT value means this column has the PT value, that's why we need to calculate the percentage of tension steel reinforcement. So our PT value which we got was 0.89. So 0.89 means it comes in between 0.75 and 1. 0.75 and 1. So for 0.75 we have the concrete value, that is 0.56, and for 1 we have the value 0.62. So by taking this value and with the help of the interpolation method we will calculate the tau C value. So the values I have written here, 0.75, the corresponding concrete value is 0.56. So for 0.89 we need to calculate now. For 1 we have the value 0.62. So for calculation of tau C by doing the interpolation method, so now first we have to take the 0.56 because this value goes on increasing. So 0.56 plus greater value minus least value, that is 0.62 minus 0.56, and greater value minus least value, that is 1.00 minus 0.75 into the value which you want to find minus the least value. So that is 0.89 minus 0.75. So after simplifying we'll get tau C value as 0.59 Newton mm square. This is how the interpolation is done. So next step is to comparison of tau V and tau C. So tau V value we got was 0.66 Newton mm square and tau C value we got was 0.59 Newton mm square. So by seeing these two we can conclude that our tau V value is greater than the tau C. So when tau V value is greater than tau C, we need to design the shear reinforcement. So for calculation of the shear reinforcement, again we'll go for IS 456 2000 code book. So as per clause 40.4 page number 72, what it says we'll see. So page number 72, clause 40.4, design of shear reinforcement. So when our tau C exceeds tau C, that is nothing but when our tau is greater than tau C, shear reinforcement shall be provided in the form of following. in any of the following forms. That may be vertical stirrups or bend upwards along with stirrups and inclined stirrups. So when our tau b value is greater than tau c, we need to provide the shear reinforcement in any one of these following forms. So next, here what they have given. For shear reinforcement shall be provided to carry a shear equal to Vu is equal to tau c into Bd. The strength of shear reinforcement Vus shall be calculated as below. So for calculation of Vus by using this formula, that is for vertical stirrups. For vertical stirrup, we use the formula Vus is equal to 0.87 Fy ASVD divided by SV. By using this formula, we will calculate the vertical stirrups. So now we will go for the calculation of shear carried by concrete. For that we have the formula Vuc is equal to tau c into Bd. So tau c value we got is 0.59, B value is 300, D is 350. Substitute all the value. After simplifying, we got our Vuc value as 61.9 kilonewton. So next is the calculation of shear carried by stirrups. For that we have the formula Vus is equal to Vu minus Vuc. So Vu value is 70.2, Vuc value is 61.9 we got. So after simplifying, we will get our Vus value as 8.3 kilonewton. So now we can go for the design of spacing of stirrups. Spacing of stirrups should be calculated. So this formula is given on page number 73. I have shown. So Bus is equal to 0.87 Fy ASV divided by SV. So now we need to design the spacing of stirrups SV. So I have moved SV to here and I have rearranged this formula. That is SV is equal to 0.87 Fy ASV divided by Vus. So here what is unknown? We have the value of Vus, D and Fy. So what's unknown here? ASV is unknown. So for that calculation of the ASV, again assume two light vertical stirrups of 8 mm pi bars. So ASV is equal to 2 into pi by 4 into 8 square. After simplifying, we will get ASV value as 100.53 mm square. So now substitute this value in this equation. So SV is equal to 0.87 into 415 into 100.53 into 350 divided by 8.3 into 10 to the power of 3. Substitute all the value. After simplifying, we will get SV value as 1530.5 mm. So again there are two rules which is given on page number 47 and 48. I will show. Page number 47, maximum spacing of shear reinforcement. The maximum spacing of shear reinforcement measured along the axis of the member shall not exceed 0.75 D for vertical stirrups, D for inclined stirrups at 45 degree, where D is the effective depth of the section. So what they have said our spacing of stirrup for vertical stirrup should not be greater than 0.75 T. In no case shall the spacing exceed 300 mm. And they have said minimum shear reinforcement. These two criteria we need to apply. The first one is our SV value should not be greater than 0.75 T, and second is our SV value should not be greater than 300 mm. So SV should not be greater than 0.75 D, which is given on page number 47. So SV is equal to 0.75 into D is 350. Substitute all the value. After simplifying, we will get our SV value as 262.5. So I am making it approximate value, that is 250 mm. So second rule is our SV value should not be greater than 300 mm. So that is nothing but SV is equal to 300 mm. And our spacing of stirrup should be least of these three. So which is least? 250 mm is least. So I am providing SV is 250 mm. And so provide two legged vertical stirrups of 8 mm pipe at 250 mm center to center. So this is how we calculate the spacing of stirrups. So our last step is to calculation of the development length. So it's cantilever beam. Now we have to provide development length. So as per clause 26.2.1 page number 42 of IS 446-2000, we'll see what it says. So for development length of bars, the development length LD is given by the formula LD is equal to pi rho s divided by 4 into tau BD. So where pi is the nominal diameter of the bar, rho s is a truss in bar at the section considered at design load. Tau BD is design bond truss. Tau BD is design bond truss. Rho s is truss. And or pi is the diameter. So they have said something. For deformed bars conforming to IS 1786, these values shall be increased by 60%. So what they have said, for deformed bars, that is nothing but HYST bars, the value is increased by the 60%. So it means, so our grade of concrete is M20. So for M20, the tau BD value 1.2 Newton per mm square. This value is again going to increase by 60%. So the formula I have written here, rho s is 0.87 Fy. So as per cos 26.2.11, tau BD value is 1.2 Newton per mm square. So and for it is deformed bars, the value is again going to increase by 60%. So that's tau BD value is 1.2 into 60% is nothing but 1.6. So substitute all the value in equation, that is 0.87 into 4 and 5 into 20 divided by 4 into 1.2 into 1.6. So after simplifying, we'll get our LD value as 940.23. So I'm making it approximate. I'm taking it as 950 mm. So this is how we calculate the development length. So this is the last step of our problem. So next is the drawing of reinforcement. So this is the drawing of our problem. So this is the cantilever beam. So one end is fixed and another end is free. So the beam is having the overall depth of 400 mm and clear span distance it is 2.5 meter. And it has the vertical stirrups of two-legged vertical stirrups of 8 mm pipe bars at 250 mm center to center. And these are the vertical stirrups, and this is the 3 numbers of 20 mm pipe bars at tension zone, that is top side. So cantilever beam tension zone comes upper side. So this is the 2 numbers of 12 mm pipe bars. This is the anchor bar. For development length, it comes here. It comes here, that is 950 mm. So our overall depth of beam is 400 mm. So we can't provide 950 mm. So that's why I have bent 2 times here, 90 degree here and 90 degree here. This is a longitudinal section diagram of our cantilever beam. So now we'll see the cross section diagram of cantilever beam. So at tension zone, 3 numbers of 20 mm pipe bars, and this is the stirrups, and at bottom side 2 numbers of 12 mm pipe bars, and the beam is having the width 300 mm and overall depth is 400 mm. This is a cross section diagram of our cantilever beam. So I hope you understood. If you like the video, so like it, share it and subscribe for the more videos. Thank you for watching.